Okay, so we've been touching the convergence and stability like throughout the semester, but now I think we'll do it a bit more thoroughly. So what is really convergence and stability? Well, common sense interpretation is that it works. When it's convergent and it's stable, the solver works, basically. So why do we have to look at this? Well, mathematically, we have infinite amount of numbers on the number line. But on a computer, we don't have infinity amount of RAM, so we need to discretize this. Instead of having this continuous line of numbers, have discrete points. And then you can get all philosophical. Is the universe really continuous, or is it made out of small packets? Think Planck lengths. Anyway, that's side point. So A and B, and part of these real numbers, in our case. Problem here is when we go from an infinite, well, actually infinitely uncountable number amount of points to a finite number of points, we introduce an error, some approximation error. So, an example, I've used this before. Here. That is the truncation error you've been seeing. So, for instance, forward plus u, bit of repetition, x plus h of x, h. So that's the approximation, but equal to the analytical derivative of the function plus some kind of error term, h over 2 factorial, second derivative, u, third, no, 3 factorial, and so on. These last terms, or infinite amount of terms, the error in our approximation. The problem is that we don't always know these derivatives of the function. So, thinking about this, what is stability? Well, if a solver for either ODE or PDE is stable, then the error we introduce in each step shouldn't amplify. PDE PDEs such a way that it explodes. So the error term is small enough that it doesn't grow exponentially. So in one step, it might introduce a positive error, and the next it might introduce a negative in error, and it will fluctuate some kind of value. And proper terms, volts. And you saw an example of this in solving the, you saw was just up and down, up and down, up and down. just exploded, and you get infinities. Practice. Stable methods tends to infinity. Okay, so that's stability. What about convergence? Well, it could be that our solver is stable, but it doesn't really converge to the true solution. So, final solution should make sense. And how do you know if it makes sense? Well, you have to trust your senses. Try to analyze the problem, just not, oh, it's giving me an answer. You have to kind of interpret the answer. Is this a good answer? A note. This could be parameter dependent. It could be that your solver converges for one set of parameters, but not a different set of parameters. Converge for one set of parameters, but not another. So if you have a solver that works for, let's say, macro scale, it might not work on macro scale, depending on the method you're using. Convergence is related to stability and so-called consistency in solver. So for ODEs, we will use a test problem to showcase this. Right. So test problem. We will use u of the differential derivative of u with respect to t is kind of lambda of t t. We are given the start condition that u of t0 number eta. There's a slight different notation that we used earlier, but that's because I'm following the note that's on Blackboard. I think it's note number 2 on convergence and stability. It's just different symbols. It's the same theory. Okay, so the exact solution to this problem is presented by something called Jimenez Principles, or analytical solution. Then you might ask, why should we solve ODEs if you already have a way of solving them politically? Well, oops. By Ahmed. That's for these kinds of differential equations. There are, of course, more variations of ODEs than just this one on the blackboard right now, which is why solving them numerically is still viable. So, the continuation of Jimenez principle. So the solution of this eta times E lambda t minus starting position 0 well from E0 to E of t minus 4 E of 4 tall. So this is for using as a test of our solvers. Okay, and you already notice now that we discretize in so 2 points for discretized E. We have n of them. N. That's how far we've gotten in time here. And to reiterate, the truncation error is how much error you introduce in each step. That's the error introduced in each step. What we'll be looking at. Each step. Okay. Then we can do some analysis on this. Again, with examples. Question? No? Second derivative of x would be some kind of function of x, and x is between 0 and 1. We say that the start, so x or t, doesn't matter, 0 is alpha, the other end of 1, beta. So we have the local truncation error at j. So this isn't the same, the tau up here. This is only for integrating. Kind of a placeholder variable. This isn't the truncation error. I hope that's possible to understand by on a case-by-case basis. So the second order FD operator in this before. X J minus what actual value is at position. Or if we want to solve a problem using Euler's method, and a new example. So yeah, this is a standalone example. No, it's a new example. Of T. Again, same as over there, but now we're going to try to solve it. Of T, again, starting position at eta. Euler's method is given, or the multiplication error of it, basically first order FD operator. I'll write this out in later. Times, so this is F as over there, the solution to the N let's see. So this method, it's basically U of T and what? U of N delta T plus whatever really at G of Tn. Equation errors. What we want to do here, for the equation to be consistent, plus or minus. So, what is a good way of saying that something is consistent with what we want to do? Well, if this truncation error in both examples tends to 0 when you have infinite spacing, or infinitesimal spacing, I meant to say, then this truncation error should tend to error, to 0. Then it's consistent. This could be a definition. Write that as a definition. Definition of consistency. This is consistent when the truncation error equation and also boundary conditions. And I'm going to abbreviate that, so BC, boundary conditions, if and only if as delta t 0, location error should also tend 0. What we're building up against is that if you have a stable and consistent solver, it is also convergent. What is the definition of convergence? F O F. Oh, let's just say it is. So UN. So this is the numerical solution at some kind of time step. At step n of u of t of n. So pinpoint that this is the u of t of n. That is the true solution. So this is the numerical approximation and this is the true solution. Again, the problem is we don't always know the true solution, so we just have to trust have versions. But sentence. U of n is the numerical solution at step n of u of n. Yes. And convergent if and only if it approaches solution when the time step is 0. n equals of t of n. Oop. So it could be convergent, but still not really a good approximation. If you try to solve one of the test exercises of the exercise 0, you have a throw. And the problem with solving, for instance, throw, a simple just throw, you can solve that analytically very easily. But if you try to solve it with numerical methods, well, specifically Euler's method, you will see that you won't hit the target unless time step is infinitely small or infinitesimal. Did that make sense? So a convergent numerical method doesn't mean that it gives you the exact solution. It only says that it has the potential to give you the exact solution. Higher order approximations will converge faster or with less discrepancy. Then again, stability is how something behaves under continuous definition as well. So that's stability. Then we have everything. Stable numerical method should, or it depends continuously. On the initial conditions. So you shouldn't, if you give it, for instance, as a starting value, just 1, it should give you 1 result, but if you give it 1.0001, it shouldn't give you a widely different answer. Basically what this says. And then, if we have consistency, plus stability, we have convergence. Stability, convergence. Consistency is often easy to show, stability harder. So we'll take Euler's method as an example of this. This is something you can think about while solving the project. Your solution is actually stable. The thing with hyperbolic PDEs is that if you solve them incorrectly, that will blow up pretty quickly. So you will see if you've done an error. Yeah, that one's right. It's one of the easiest way of solving an ODE. Oh. We will have, for the previous problem, a view of 1 n delta t of n via n. Again, numerical subscripts. Okay, then we need the local multiplication error of this. It's basically a Taylor expansion. Tn. That's Tn big O delta T. Q divided by N. Give us okay. This is a half delta T Q skipping something here. Anyway, plus big O delta T squared. So is Euler's method consistent? When delta T tends to 0, does the truncation error or local truncation error also tend to 0? Well, when this tends to 0, this will go to 0, and according to big O notation, well, if this is almost 0, then this is most certainly almost 0. It's consistent. There we go. This method is consistent. That's good, but it's still not convergent. Still missing one thing. And that is stability. Or if we actually show that it's convergent, show that it's also stable. Because again, stability is difficult. Good. So this is the local truncation error. Now we'll look at the global error of this. List. Tn1 analytical over T Tn of Tn. So if we solve this equation for Tn1, one plus lambda the T the truncation error. Okay. And then if this is the analytical solution, this U of P of N1. We look at the difference, so numerical one, UN plus 1 minus this one. we should get U of n plus delta t d for U of n plus 1, same solution that we have here. Now we try to subtract this part. E of n, as it's subtracting, it's going to be minus delta. Well, no, delta t and we go total of n. Looking at this, we see that the error in each next step is, well, lambda. Yep. Previous minus station error. T. No, T2 over this. Mm-hmm. Have been E plus 1. Further this is defined as the global error. Looking at this, we see that it's based on the previous one. In this method, we will introduce more and more and more error. So now we have a recursive relation for it. Solving it, so by induction we can go all the way to the starting point here from T0, and I'll skip the details. What we will end up with that the error at time step n 1 plus t lambda power of n times the error of the first time step minus delta t m1 n 1 t lambda m tol minus 1. So, if this is to be convergent, the global error should be bounded. It doesn't explode. We go from analysis that 1 plus delta t lambda is always going to be smaller than delta t. Lambda meaning that this term plus delta t m e delta t lambda smaller than just n times delta t lambda. This n is smaller than e of constant n t smaller than this big T, so the time in all. This is just analysis. The main point here is that this bit here smaller here. Yep. This. Okay, so this is known. This is known. We just assume this is known, is taken from analysis. So if you have both sides and you raise them to n minus n power, so then this is just raised to the n minus 1 power. This is also raised to the n minus 1 power. Okay, so it's still the same. And then we say that n minus m, well, that's smaller than just n, because we don't do any minus. And then we say that, oh, this is just some kind of time t, because n times delta t. And we don't really need this last step. This is just to get it on a nice form. It will show us that this error is bounded at the end. And then when the global error is bounded, then it's a convergent method. So this is just a sidetrack, basically. It seems like very weird logic, but it holds up and it makes stuff easier. So, using what we have over there, of n plus t lambda n times e0 minus the whole thing again plus 1 n t lambda minus m times 4 minus 1. And now we can apply what was over there. This is going to be smaller than e t lambda times value of e0 plus delta t minus 1 again smaller than t lambda 0 and the t and then the max. This error and this here is always smaller than big T as we defined it last time, so we should stick with me for a few more minutes. Yep. Yes. But this formula. So this is the global error. Okay, so we found out an expression for this over here. And then that is the difference in the numerical error and the numerical solution and the analytical solution. So the difference in those two. So basically the global error, because of the numerical approximation, introduces some kind of error. And then we're trying to show that this error is bounded, that it doesn't grow to infinity. And then we need to apply some tricks from analysis, what is on the right-hand side over there, and basically just applying it to it. Yes, the problem there is that you don't really have the analytical solution. It's difficult to get this. You can do it in a homogeneous medium, but if you have an inhomogeneous medium, well, I mean, you can also do it in layered media, but if you have some kind of medium you don't really know what it is, then you can't really do this. So this works for Eulers because we can actually solve it analytically. Well, in the case we given here for this, because we say that this is the analytical solution, and then we can do this. When we can't do this, then we can't really do it. Then we have to show it in a more intricate way, or just assume that we have a homogeneous medium, show that it's convergent, and then hope for the best in an inhomogeneous medium. Basically, there is some belief going on there. I mean, it's founded in math, but maybe we should have a 15-minute break since we're over time, and then I'll do the climax after the break.